To introduce our next speaker, Oliver Riordan. Oliver is a professor at the University of Oxford and a fellow of St. Edmund's College. He's no stranger to Cambridge. He spent there quite a few years, did his PhD here, and for many years he was a fellow of Trinity College. He has done an awful lot of important work on a great variety of topics, on extremal combinatorics, on polynomials of graphs, on percolation, bootstrap percolation, the evolution of random graphs, limits of graph sequences, especially those of sparse graphs, and so on. Today I asked him to talk about a beautiful result he proved a little while ago with Lutz Warnke about the phase transition in the Achlioptas process, which was quite a sensation when it burst on the scene. Oliver.
Thank you, Bela, for the invitation to speak here. Listening to previous invitations, I was hoping Bela wouldn't mention my thesis title and get stuck, because then I wouldn't have been able to remember how it finishes. But since Bela supervised it, he also doesn't remember the title. We know what it was about, but just not what the title was. I was also going to say why I've chosen the topic I've chosen that Bela's told you, namely he asked me to talk about it. So this is, Lutz and I have done quite a lot of joint work on Achlioptas processes, some of it less technical some time ago, and some more recent thing which is more technical, and I'll mention the more recent thing briefly, but we'll mostly talk about the less technical bits, because I hope that's suitable for the audience. And if you know it before, then sorry. And Lutz is a research fellow here in Cambridge who will be going to Georgia Tech very soon. Okay, so the basic background for all of this, which I assume is familiar to most of you, but I'll go through very quickly, is just the classical random graph process. So you have a fixed set of vertices, n vertices. You put edges in one by one in a uniformly random order. So each time the next edge is just uniformly random among all the edges that are not there. Okay, and if you have put in m edges, then you just have a graph on n. So the vertices are labeled. They're say the vertices 1 up to n. You just have a graph on n vertices with m edges, and all possibilities are equally likely. And this is the most studied random graph, or this and its cousin GNP, where you put in edges independently with some probability, which is essentially the same, are the most studied random graphs since Erdős and Rainey started this area more than 50 years ago. And what can one say about them? Well, one of the most interesting things is the phase transition in the component structure. So for these questions, the scaling is the number of edges will be linear in the number of vertices, and I'll tend to write it as t times n, so thinking of t as a time parameter, just a number of edges divided by n. If you take 0.49 n edges and 0.51 n edges completely at random, if you just drew those, you wouldn't see a difference. There's just uniformly random edges. One has a couple of % more than the other. What's the difference? Well, if you look at the component structure, there's a very big difference. 0.49 n edges, what are the components like? They're all small. There's a kind of exponential tail, and the biggest one has logarithmic size. 0.51 n edges, you have the same picture, this exponential tail of small components, but now there's also one big component, a giant component, which has a macroscopic size, so size proportional to n. And Erdős and Rainey showed this in 1960, along with lots of other things. This is a very crude summary. They told us not just logarithmic, but what the constant is, and so on and so on. What comes next? Oh yeah, here's a plot. So this is the rescaled size of the giant component. So the biggest component, L1, will be the number of vertices in the biggest component. Take that, divide by n, and plot against time, which is number of edges divided by n. Of course, it's a random process. You have a random curve for each n, but in the limit, the random fluctuations disappear, and also there's a limit which is independent of n when you scale this way. And we know everything about this. It's a nice analytic function, except at that corner. Okay, what next? This is more than 50 years ago. You could ask more details about this particular phase transition, or you could say, okay, this is one particular model, what happens in other models? So to briefly mention the first, if you look at this picture, there's an obvious most interesting point, which is here. So the question is, sort of, I say it's an obvious question, but it was 24 years until anyone asked it, namely Bela asked this question. What happens if you zoom in here? Zoom in by a constant factor, nothing very interesting happens. So the Erdős-Rainey result tells you what's going on sort of near there if you go a constant n edges away. So if you move a constant time away, then we know what's going on. This 4 is the slope of this curve as you approach the critical point, and we know what the scaling is from both sides. But Baylor asked the question, okay, but what about zooming in a way that's growing with n? So when do things change? And he also essentially completely answered this question as well with a small gap in the range of parameters, which was filled in later by Thomas Wittschek in 1990, and says if you zoom in by at most n to the 1/3 or less than n to the 1/3, then you see the same behavior, and beyond that you don't. So at the corner, there's the real scale of what's going on the corner. It's not completely sharp, but the scale is at the level of n to the 2/3, and outside that, it still looks like a sharp corner. Okay, there's lots more to say about that, but I won't really. In the other direction, different models, this is just some random list. I think in this context, you all know this phase transition is just it's a basic thing that underlies thinking about any kind of phase transition in any context, more or less, so especially in random graphs, but lots of other contexts. It's not the same as any other one, but it's what's going on here is sort of one of the basic mechanisms that's present in, almost infinitely many other contexts, and these are some examples. So if we look at particular random graph models, here are some corresponding curves. So again, the giant fraction of vertices and the giant component against time, against the edge density for various random graph models. These are all within the general inhomogeneous model that Baylor and Svante and I wrote down, but particular cases. And you can see things look quite different. So this curve, actually, the critical point is at 0, but these others are not, and you have just sort of different types of behavior, how this curve goes. That's not surprising, because you can write down infinitely many different random graph models with almost any property if you just say, invent a new model. So if we allow ourselves to change the model as much as we like, then of course we can get a huge variety of completely different behavior. But that's not surprising. What about if we only change the model a little? And I think this was a question that Dimitris Achlioptas asked in around 2000. I don't know exactly what he was thinking, but this is a way of motivating his question. His question is slightly strange. It's very, very nice. It leads to lots of lovely mathematics, but the first time you say it, it's an odd thing to ask somehow. So another bit of motivational background is a phenomenon in a completely different context, which is the power of two random choices. So you can think of this in the context of balls into bins. You're distributing things into balls into bins, or slightly more seriously, allocating, say, tasks to servers. You want to do it reasonably uniformly, but it's too expensive to all the time look exactly what the current situation is, what are the loads on all the servers. A pretty reasonable strategy is just totally random allocation. Say you have n servers and n tasks, or order n tasks, doesn't matter. If you just allocate them randomly, you'll get a pretty even spread. Okay, but not exactly even. And the maximum load you'll see anywhere will be essentially logarithmic order. Okay, what if you allow yourself to move a small amount away from totally random? So you do the minimum extra amount of work, you pick 2 servers randomly, and you look which of those has the lowest load, and you allocate the task to that one. So you're doing it one by one, with tasks come along one by one, each time pick 2 servers randomly, ignoring the current situation, then look at those 2, and allocate the task to the less loaded one. Okay, and Azar, Broder, Carlin, and Upfel in the 1990s showed that this brings the maximum load down to log n, okay, which compared to what it was is a sort of exponential reduction in some sense. Okay, so Achlioptas' question was, what happens if you do this in the context of the random graph process? So you're forming a random graph, step by step, adding edges. What if instead of each edge being completely random, it's one step away, we have 2 random edges, and we choose between them in some way? Can we delay or accelerate the phase transition? So I sort of told you what the model is already. Here's a picture. We have a current graph in black. 2 random edges come along. We choose one of them according to some criterion, some rule, and we add it to the graph. Okay, and then we repeat. I only have one slide, so I won't repeat the slide. I don't know why it didn't. Here's the formal definition. There's no point reading it. It just says the same thing. We have the current graph. At the nth step, we have 2 choices, 2 candidates for the next edge, which are uniformly random, and we select between them according to some rule. what kind of things might the rule do? So, in general, it could use all information about, it's not allowed to see the future, because it's supposed to be a step-by-step choice. But in general, it could use all information about the past. So these are labeled, the vertices have labels, so we could say, well, I'll pick the first edge if the sum of the numbers on the vertices is prime or something. But that's sort of silly, and in the end, we're interested in looking at how the component structure of the graph evolves. So it would be nice if what we use to make our decisions is just the component structure. It should certainly just be something, some graph invariant, but it's nicest if it's just the actual sizes of the components. So here's the current graph, here are the two candidate edges. The rule doesn't see the whole graph, it just sees how many vertices are in each relevant component. So there are at most 4 relevant components, the 2 edges of the 2 ends. It just sees these numbers, 1, 5, 3, and 2. Okay, that class of rules is called a size rule, and there's a further restriction, which is bounded size rules, and a bounded size rule is a size rule except with sort of one too many counting. So there's some cutoff. So if the cutoff is, say, 3, then the rule sees this component is size 1, or it's size 2, or it's size 3, or it's size 4 or more, but it doesn't know the particular size. And sort of exaggerating slightly, 99% of results are about size rules, because those are the natural interesting ones. And of those, about 90% are about bounded size rules. And the reason for that is sort of because they're easier. Except that's not really, I mean, that sounds like a cop-out, but it isn't. So, I mean, for example, in percolation, there's lots of more work done on percolation in 2 dimensions than in 3 dimensions, even though 3 dimensions is really the most interesting physically. And that's not just, I mean, it's partly because we can't do in 3 dimensions the things that we can do in 2 dimensions. But that doesn't mean the 2-dimensional work is not interesting, because the 2-dimensional work, because it is accessible, we've gone very far with it and got all these results about continuum limits and so on and so on. So it's not, that's not putting down the work of bounded size rules. Okay, they're easier as a class, but that means we can go further and we can get interesting mathematics studying them, just like in 2-dimensional percolation we can get interesting mathematics. Okay. Yeah, what rule might we choose? So suppose we were trying to accelerate or delay the phase transition. If you have a graph, it doesn't yet have a giant component. How do you measure how close you are to having a giant component? You could just say, well, how many vertices are in the biggest component? But that's somehow much too local. This is why does it matter whether you've got one that's got log n or 2 log n or something? That's not really a good measure. A much better global measure is what's called the susceptibility, which is basically the sum of the squares of the component sizes. And it's the same as saying, pick a vertex of the graph at random. On average, how big is the component containing that vertex? Okay, and this comes up in lots of contexts, either in random graphs or in classical percolation, and it's a quantity that as you put in edges, it increases, and it tends to diverge, it goes to infinity at the critical point where the giant component emerges, usually. So how big that is a reasonable measure of how close I am to having made a giant component. Okay. So, if you're trying to delay or accelerate the giant component, you could think about the susceptibility. So if you merge components of size a and b, you replace a squared plus b squared by a plus b squared, so the change is proportional to ab, to the product of the sizes of the components you're merging. So Baylor suggested right at the beginning, if you wanted to, say, delay getting a giant component, you should, among your 2 choices, pick the one with the smaller product. And this is called the product rule. Okay. Which is a size rule but not a bounded size rule, and it turns out to be difficult to analyze. So in terms of early rigorous results, if you want to accelerate the phase transition and you allow general rules, it's a sort of easy exercise to find a rule that does that. So if you know all this, you can try to find one in the next couple of minutes. But for delaying is not so easy, but it's still not very hard. And to actually prove something, rather than look at the most interesting rule, just look at the simplest rule, and that's what Bowman and Fries did. They took a very, very simple rule. Look at the first edge. You prefer to join things that are small at the moment, so the first edge, just say, if they're both size 1, these vertices are currently still isolated, then connect them. Otherwise, well, take the second edge. Okay, and in the other direction, you can do the reverse, where you join the first 2 vertices if neither is isolated. Okay, so they rigorously proved that these do shift the critical point of the phase transition, and these are these limiting curves for these three rules. Okay, that's all very nice. So the answer is yes, you can shift the critical point of the phase transition, but it seems to have more or less the same nature, which I'll previously come back to. But what about the product rule? What's the curve of the product rule look like? And the answer is this. It's the purple one. So it's shifted much, much later, but also something completely different seems to be happening here. And this plot is slightly misleading, because if you take the data points from this plot, but these are all from simulations that Lutz did on. So in this area, some people seem to simulate graphs with about 1 million vertices or something, but it's very easy to go, if you think about it a little bit, which Lutz and I did, it's quite easy to go a lot beyond that. So these are all simulation of graphs with 10 to the 11 vertices or something, which is, sorry? 10 to the 14, okay. Right. 10 to 11 sounds easy to me, 10 to 14 sounds hard. Okay, but Lutz has done that, so, okay. If you look at the data behind this, there's some points 0, 0, 0, 0, 0, 0, 0, 0, and then the next point is somewhere there, and it's disjointed with a straight line. Okay. Actually, that something like this was going on was suspected right from the beginning. So I presume it was Achlioptas himself suggested it, and Baylor and I remember thinking about this, that there's actually a jump in this product rule, and we tried to work on this for a little bit, trying to prove that this jumps, although we didn't get anywhere. That was a long time ago. And then we forgot about it. I think some other people thought about it a bit, but everyone sort of forgot about it until it was came to prominence again when Achlioptas, D'Souza and Spencer published it in the journal Science, which is quite unusual for something that's mathematics. And what they published was a conjecture. So, yeah, not a mathematical result, but a mathematical conjecture that this rule has a discontinuous transition, that this limiting curve actually has a discontinuity at the critical point. And they even put sort of specific numbers on it, so that just says that in little o(n) steps, it jumps from no giant component, size little o(n), to some positive constant times n. And in fact, their positive constant they suggested was about half, or bigger than a half. So it jumps from something very small compared with n, in particular, say root n, to something very comparable with n, at least n over 2, in a pretty small number of steps, about n to the 2/3. Okay, this is based on simulations and extrapolations in some reasonably sensible way, which they called conclusive numerical evidence, which is a phrase that doesn't make sense to a mathematician. And it's called explosive percolation. It's very exciting. You don't see these discontinuous transitions in this kind of model, and got lots of citations and lots of physicists explained why it happens. One group of physicists said, no, actually no, it's not discontinuous, and they gave a heuristic explaining that. I was not convinced by this because their argument is very, very explicitly circular. So they start by saying, assume the transition is continuous, then we can calculate some things autoheuristically and blah, 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 some significant work in it, and we get something, and this is consistent with what we have, so therefore the transition was continuous. Okay, but yeah, okay, still. So I certainly didn't believe this at the time. Now, oh yeah, sorry, I have one more slide. So why should this explosive percolation happen? So the idea is that the rule is suppressing the formation of large components. So this is a picture of the component size distribution. I'll show you something on the board to the side. So if we have lots of vertices, if we have vertices and components of size around S, how do you make a bigger component? You need to join one of these with something else. Okay, so for example, something in here with something else. And suppose there's about alpha n vertices here, then in the Erdős-Rényi model, the probability you do this is about alpha, that your edge will hit this set. But in this model, because you like making small components, you have two candidate edges, and if one is here and one is outside here, then you'll pick the outside one. So to actually join something big to something else, of your two choices have to have one end inside here. So the probability in one step is alpha squared, not alpha. Okay, So that means until there's a decent fraction of vertices in size at least s, you'll have a very small rate of making things bigger, say about size 2s. So that says you won't get many in size bigger than 2s until you've got actually quite a lot in size bigger than s. So you'll build up a significant number of vertices in components whose sizes are comparable, and as you approach this phase transition, this size range is getting quite large, and that's roughly what you see in this picture. So this is component size on a logarithmic scale, so these are very, very big components, but still small compared with n, and we're seeing that there's this bunching effect that's producing the discontinuous transition. And now hopefully the screen will magically disappear, and I will continue to explain on the board. But it seems a pity not to use these very nice boards to give an actual argument. So let's try to prove that there's a discontinuous transition. Well, let's try to understand it. So let's start. So I'm going to do something that may seem circular at the beginning, which is let's assume there is a discontinuous transition. Let's investigate its properties. And the idea is if we know what's really going on, if we could figure out what these curves really look like, probably we could prove it, because we know the equations for how things evolve. So if we knew what the solution was, we could probably prove it. Okay, so let's start by assuming we have this discontinuous transition. So we've got this L1 and we've got this number of steps. Okay, so and here we've got, say, a certain number of steps, and at this point we've got some very big component. So this L1 is at least some constant times n. Okay, but we also know that up to here it's very small. So if you go any epsilon n steps, so m plus minus epsilon n, for any constant epsilon, then we know the biggest component has size little o n. Okay, so let's think about how this big component arose. So at the time m plus, we have a very big component. So that's Cn vertices that are a single component at time m plus. Let's go back epsilon n steps and see what happens. And there's small components outside. So if we go back, we're deleting edges from the graph, some in here, some in there. When you delete an edge from a graph, what happens to the components? So either nothing, if the ends are still connected, or a component falls apart into two components. Okay? So if we delete epsilon n edges, so I guess changing color, then what we know is inside we deleted at most epsilon n edges. So how many components do we have inside? So there's sort of, I'm drawing the bigger ones at the top and then the smaller ones go down. And what we know is at the time m plus minus epsilon n, we know there's at most epsilon n plus 1, which let's ignore that, components. Okay? That together will form this big component of Cn vertices. Okay, what size are these components? Well, a significant fraction of the vertices must come from reasonably big components. So let's draw a sort of cutoff line here, where below we have the individual components of size at most k. Let's ignore this stuff. So here we've got components, and the individual ones in the bottom have size at most k, where k is, say, c over 2 epsilon. This is a bit vague, so ignoring rounding to integers and so on. Okay, then here we have at most epsilon n components. Each one has at most c over 2 epsilon vertices. So how many vertices are here? At most cn over 2. Okay, so up here we have at least cn over 2 vertices. So this is all that, this is at epsilon n steps before this big component is there. Okay, that was going backwards in time. Now let's try to go forwards. So let's forget how we got this picture, and let's just say we start with water razor. We start with some situation where we have some constant n, let's say bn vertices, and these are all in components of at least some size k. Okay, what happens when you run forwards in time? Well, you will be forced to, whatever the rule you choose, you will be forced to join these components at some kind of reasonable rate. Okay, why? Well, if you get your two candidate edges, and if both edges are somewhere inside this big blob, then you'll certainly choose an edge in the blob. Okay, what does that happen? How often does that happen? Well, in each step, the probability is at least b to the 4 that all 4 ends of these edges are inside the subset of bn vertices. Okay, so picking an edge in whatever this set is, U or something. Okay, it may not cause 2 components to join because it may be inside a component in the current graph. But from the picture I just rubbed off, if we stay before this m plus, then we're assuming there aren't any very big components. Okay, so let's look at in the next, say, epsilon n over 2 steps. So within that time, that's before the giant component emerges, and we know that all components are very small, it's then very unlikely that an edge is inside a component. Think about the first end of the edge. For the other end to be in the same component, well, the biggest component has little o n vertices, so it's probably probability little o1 that the other end is in the same component. Okay, so that's just very unlikely. So let's sort of decrease this a little bit, so at least b to the 4 over 2 of actually joining distinct components for in U or meeting U. I mean, they can get joined to things outside, but that doesn't actually mess things up. Okay, so what can we conclude? Well, how many times will this happen? Well, overall, it will happen epsilon b to the 4th over 4n times components will join up. But how many components are there? Well, at most, the number of vertices, bn, divided by k. So we get this inequality, because we know that, I'm skipping over some details, but not very much. So this often we will merge 2 components meeting the set, but there weren't very many components meeting a set to start with, if k is large. Okay, so the conclusion from this is that this k is at most something, or whatever it is, some constant, which happens to be b to the minus 3 over 4 times 1 over epsilon times 4. Okay. That, of course, is, if you plug in the numbers here, this little k and c over 2, that's consistent, that's no surprise, but you don't have to change the numbers very much to make it inconsistent. Okay, so if we had, so let's pick another cutoff here. I'm not sure what my color scheme is now. So, but let's suppose, so if we had, so this is going to be some big constant, so capital K is going to be some big constant times little k. Okay, and if you look at the numbers, if we just choose this constant big, then this goes wrong, because k scales as 1 over epsilon, little k, so if you put in a big constant here, this is not true. Okay, and that doesn't, and for b, any constant. So the conclusion of that argument is that in this section, there's at most, say, cn over 4 vertices. If you put a big constant here, then with b as c over 4, we get a contradiction. So there's at most cn over 4 vertices, the components of size larger than k. Okay, so here, this is the powder keg, right? We've got the components with size k up to just some constant times k, and the number of vertices here in this powder keg is at least, it's a constant n. And that's, this is sort of the picture we were trying to establish. Okay, so far we're still trying to prove that there is a discontinuous transition, but then we notice something, which is this is at a time a little bit before the transition, before m plus. But these components, how long do they survive? Well, a component has a half-life that's order n over its size, because if you just have a component with size s vertices, then as long as all the candidate edges are outside, then you just won't join this component to anything. Okay, so let's run forward epsilon n steps, and then let's see how many of these survive. Well, a component of size at most dk survives with at least some probability like this. Again, the exact formulae don't really matter. Epsilon n. That's the probability it survives up to this starting time m plus. Okay, plug it in. That turns out to be constant. Okay, so what's the conclusion? It's that at the critical time m plus, at time m plus, we have at least some tiny constant n vertices in components of size between k less than size less than constant k. What was k? K was anything. So that's a contradiction. You just think about size 1, d squared, dot, 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 however many bins you need, up to, say, 2 over gamma, and there's supposed to be, in the limit, gamma n vertices in components with each of these size. That's more than n vertices. Okay, let's get some details, but not really many. For the basic result, that's the proof. So now going back to the slides. That is actually the order that went through. So despite this other heuristic result saying it was continuous, we were trying to prove it was discontinuous by getting a good idea of the picture. At some point we realized our idea of what's happening in the discontinuous case is sufficiently detailed that we can deduce faults. So therefore the transition is actually continuous. And the argument isn't circular, because it was a... Right, so that's the result from now 5 years ago, that every Achlioptas process has a continuous phase transition, which we managed to publish in Science, which is unusual. They don't normally publish 2 papers on the same topic, even if the second one contradicts the first one. But we managed to persuade them that this is not the start of some ongoing argument. This is actual disproof, so there won't be...
Conclusive
yeah.
non-numerical evidence.
Yes, conclusive logical evidence. The same argument answers various other questions. So a general question in lots of random graph models around the phase transition. Yeah?
So when you say every Achlioptas process, you mean regardless of the rule?
Yes. Yes, and it's actually a bit more general than that. This argument, you could see it was pretty robust. I mean, it just relied on the fact that when both edges are inside here, you'll have to choose one of them, and when neither edge touches the component, you won't touch the component. So it didn't matter what the rule was at all. Yeah. A version of the same thing. So often in these phase transition things, it's easy to understand sort of small components, like in Riordan, and then you have this question: is it true that all the remaining components are not in small components, whatever that means, or in a single giant component? And so a sort of modified version of the same argument shows that, which answers various conjectures of Joel Spencer and so on. And also, it means if you understand how the number of vertices and components of each small size varies, and that behaves in some sensible way, then we also know that the number of vertices in the giant component behaves in a sensible way, and in particular has a scaling limit. What am I going to say next? I don't remember. Okay, so now just to briefly say more recently, so that's a result about general rules, and what we've been doing more recently is looking at bounded size rules, and here you have this sort of phenomenon about universality in various percolation contexts, that within some range of rules, the numerical details of where the critical point is and so on seem to vary, but lots of more qualitative features of it are the same. You have the same type of scaling, and that's presumably not true for general Achlioptas processes, but it is true for bounded size rules, and that was one of the questions. There have been lots of partial results about this, but I think this is somehow probably the last word on it, and this is recent work with Lutz. This is extremely long and technical, but the conclusion there is that for bounded size rules, everything looks like Riordan, but with different numbers. Although, I mean, the properties of the process are different because you have dependence in the process, but the result is that the bounded size rules somehow are a universality class for these questions. And also technical things about the component size distribution. You have the same kind of tail behavior for the small components above and below the critical point as you have in the Riordan case. And there were lots of partial results on this and conjectures that these results sort of answer them all. But the proofs are not very simple. What about remaining questions? So you could ask, so I've sort of been plotting these limiting curves, assuming they exist. But in general, if for each n you have a random process, there's no reason that even when you scale in the right way, that you should get a deterministic limit, or that this should be independent of n. So maybe there are random fluctuations that persist. So here we have, again, some partial results. So we can show that things behave basically until the susceptibility diverges for any Achlioptas process, which is probably where the giant component emerges, but we don't know in general. This is analogous to a question of percolation. Are the two definitions of critical probability from Temperley and Hammersley the same, which in percolation we know they are, in Achlioptas processes we don't. And also there's a system of differential equations that correspond to one of these processes, and we can show if that has a unique solution, then the process has a scaling limit, but that's somehow a very big if. And there is a warning. So this is not exactly an Achlioptas process, but something pretty similar. So there's a slightly more general class of rule where instead of saying 4 vertices and you have to join either these two or these two, which is the choice between two edges, you could say we pick some number of vertices, maybe it's 4, and then you can join any pair of those according to some rule. Okay, and this is a particular rule for 3 vertices, which has very weird behavior. So the size of the biggest component, in this case, can only grow by doubling, and when you try to plot the limit, it just doesn't converge. So and this has a very, very steep phase transition, which is hard to see, but there's sort of randomness in how you get to a certain size of the biggest component here, and then the random output here sort of persists through the rest of the process. So when you try to take the limit, you get something that is random, not deterministic. And other questions. So we understand these ones very well now, these bounded size rules. In these non-bounded size rules, so these are various ones, the product rule is somewhere here. So we've shown that this curve is actually continuous, but it's still not like these. It's extremely steep. Okay? But we don't actually know that at a mathematical level. So what do we know? So if you take the product rule, so we believe that the curve has say infinite right derivative at the critical point, but we can't prove that. And you can answer, what should the behavior be? If you go epsilon beyond the critical point, how big is the largest component? I'm very nearly finished. So then the physicists expect, and I'm sure they're right about this, that it scales as a power of epsilon. So in the Erdős-Rényi universality class, the power is 1. It's linear with epsilon. But here it's some very, very small power of epsilon, which explains why it looks discontinuous. So to get up to, from n to n over 2, to 0 to a half in the scaling limit, you need epsilon to be about 1 over 2 to the power 18, so 4 millionths, which is why the curve is why it's hard to see that it's actually continuous. But still, this power scaling, we don't know it from either side. So we have some upper bound from our proof, but it's not very good. It gives a bound on how steep it can be, but it's a rather weak bound. And we don't have any lower bound that it's actually, that the derivative is infinite at the critical point. And I think that's the end.
Thank you very much. Are there any questions?
Do you have any result on the fractional percolation process that you are showing in the last slide? I mean, it's like
this
yeah.
one. So no, this is from simulations and heuristics.
Okay.
So we're pretty sure that's what's happening, but we can't prove it. And there's a less natural case, which I maybe have a slide for, which is this is the Erdős-Rényi process, but you modify it slightly. It's not a size rule. It's sort of kind of cheating. It depends. If you allow general rules, it's not cheating. You just say, you look at the current graph, are the two biggest components the same size or not? And then do something in one case, something in the other. And that has this behavior. We can't prove this either, but I can imagine being able to prove this. Whereas the other one, I've got no idea. I think this might be provable, but it's not as nice a process. Whereas the other one, I don't know.
Yes?
So is there a noticeable gap between when the product rule appears to delay things versus the rigorous lower bounds on how long we can delay things? Or does your differential equation approach allow you to get arbitrarily close by just integrating
That is
your system?
some work. I've forgotten who was it who looked at these approximate versions, cutoff versions. Look is here to answer all the questions. There's some paper, let's maybe remember who the authors are, looking at approximate versions.
Results on the
Okay, but there is a method that would give something. So it's presumably the case that if you take a bound-sized rule that approximates the product rule, then you can get the critical point as close to the one of the product rule. And for each bound-sized rule, you have some system of differential equations. You won't have an explicit formula. It'll be the blow-up point of that. And if you want a good bound on that, you could do, in principle, do sort of interval arithmetic or something. So it's presumably, no matter how close you want to get, there will be a doable calculation that ends in a proof that there is a rule that delays it that much. If that makes sense.
And finally, what are the hopes of proving that the product rule is in fact optimal? At least amongst
That's this slide, which I now don't remember what it's about. So there's some other rule, min h. I've forgotten what that is. This is from some time ago. So I'm pretty sure that the point of this slide is that there's another rule that appears to delay it more further than the product rule.
harmonic mean or something.
Yeah. Okay. Yeah. So yes, you take the not the product, but the harmonic mean of the component sizes and minimize that or something, maximize that for delaying, whatever it is. So the product rule actually isn't best. So the product rule is a greedy algorithm saying let's minimize the increase in susceptibility step by step in the current situation, but that's not necessarily optimal globally because it'll affect the future choices. And again, some simulations suggest actually it's probably not optimal, but no one has a proof. But again, presumably,
Yes?
Have people investigated what happens on geometric graphs? Let's say the hypercube.
Yes. So there's lots of things about in the grids where in some cases you can actually get discontinuous transitions, I think. I don't know that much about them. There's something about hypercube.
Simulations, right?
There's lots of simulations. I think it's a lot harder to prove anything in those cases. Yeah.
Does it make any sense to think of, or maybe it's all behavior of completely different rules which might accelerate the position of the point, which is in this rule where you pick your vertex with probability proportional to the degree of the vertex. So you add points in that way.
Yes.
This leads to a power law of
Yes.
degree distributions. Now, could one examine? And that somehow suggests, I guess, that you might get your line component earlier.
I'm not quite sure what the question is. So that was one of the curves in the picture
okay.
with lots of curves early on. So that's this one. So BA is Darabaki-Albert scaling model. So that the critical point is at 0. This is not an Achlioptas process. So
Right.
this is not in the class of Achlioptas processes.
No, that's right.
And it does have completely different behavior. If there's some, I don't know if there's a sensible question involving mixing them together.
No. I mean, I hadn't realized that these
Yeah,
had been studied. So in fact, my question was, have these things been studied?
Yeah. And this is because they figure about the robustness of real-world networks or something. Leads to these.
Actually, let me say about the product rule that it sounds that I suggested it and then for 2 years I couldn't even prove that the giant component, the emergence could be delayed or raised, and it's not the case at all. One day, Dimitris bumped into me at Microsoft and asked me, I have a toy question. And this was a toy question. While standing, I told him, I'm absolutely sure that this product rule will do it both ways. And if you like, we can prove it. And then he said, no, don't think about it, don't think about it. So I didn't think about it. And the next I heard was that there's a paper by Bowman and Fries doing the simplest possible result. And so, it's not the first time it happened to me, and not the last. So it's not. I mean, it was just a off-the-cuff remark, and I was forbidden to think about it. With him, the idea was that together, of course. Yeah. Any more questions? Yes, please.
So for the lattice case, you have this phenomena also, like in high dimension, you are like mean field, and low dimension you have
Yes.
power law. Can we see this kind of in this case also like some kind of critical rule from which like can we see it like this, like a reduction of dimension of zero opaque?
I don't know. So we've only looked at things that are mean fields. These are all kind of mean field type models.
But would you have like some kind of rule, like when you change the parameter, then it becomes like moves from a polar law to some kind of to a linear?
So I don't think so. So in this context, basically the distinction is between bounded size rules and other ones, and whatever the bound is in the bounded size rule, then you have this linear behavior, and I think there's going to be a pretty wide class of any unbounded size rule that suppresses large components probably has this very steep transition. So that's, I don't think, I can't see a parameter that you can vary continuously there, if you see what I mean. It's just either it is bounded size or not. So I don't know, I think.
Before we thank Oliver and all three morning speakers, let me just say that now we'll have a break when you have lunch, and the next lecture is at quarter to 2. So hope you'll have a good lunch, and then let us thank Oliver and the other two speakers.